Hi student, today we are going to start new topic 12th standard physics lesson 4 electromagnetic induction and alternating current. First of all, we are going to see what is electromagnetic induction. So students, say last class we have seen magnetic effect of electric current. That is, when a electric current is allowed to pass through the conductor, it produces magnetic field around the region of the conductor. This was discovered by Christine Oersted. Later, Ampere also proved a current carrying conductor. That means solenoid, bringing us a bar magnet. That is, when we alone current pass through the solenoid, the solenoid is behavior as a bar magnet. So when electric current is allowed to pass through the conductor or coil of wire or solenoid, it produces magnetic field. So there arises the question, when current produces magnetic field, why can't the magnetic field it produce current? Understand students? Why can't the magnetic field it produce the current? So that a reverse effect, that is changing magnetic field, produces current. You know, changing the current produces magnetic field. So a reverse effect, changing the magnetic field, produces the current. So student, Michael Faraday demonstrated the reverse effect of Oersted experiment. He explained the possibility of producing induced EMF across the end of a conductor when the magnetic flux linked with the conductor changes. This was termed as electromagnetic induction. The discovery of this phenomenon brought about a revolution in the field of power generation. Understand students? Okay. Then, before going to main part of the lesson, the first part we are going to see what is magnetic flux. Magnetic flux is nothing but total magnetic field lines of force passing through the area. Understand students? Total magnetic field lines of force or number of lines of force passing through the normal to the given area is called magnetic flux. It is represented by phi b. That means magnetic flux. Phi b is equal to integral of b vector into dA vector. B is nothing but magnetic flux or magnetic field. dA is the area of the conductor. SI unit of magnetic flux, Tesla meter square. It is also measured in Weber. Understand students? Okay, now going to explanation of magnetic flux. Suppose consider a small area A. This is nothing but a area A. Then this area passing through the magnetic field of given area. So total magnetic field, understand students, total magnetic field lines passing through the normal to the given area is called magnetic flux. So magnetic flux, it is represented by phi b. Phi b is equal to phi b is equal to integral of b vector into dA vector. It is dot product of magnetic field and aerial vector. So magnitude is given by phi b is equal to integral of b into dA cos theta. This is a magnitude form. B is nothing but magnetic field. It is a constant. Area, it is a small area. Cos theta. What is theta? Angle between magnetic field and normal to the area. So in this case, phi b is equal to integral of b into dA cos theta. What is the angle between magnetic field and normal? This is a magnetic field parallel to the normal given area. When I found to the theta, what is a theta? That is equal to 0 because both are parallel to the each other. Magnetic field and normal, b vector and n unit vector, that is parallel to each other. So angle 0 degree. Therefore, what is the value of cos theta? Theta is equal to 0. Cos 0 is equal to 1. Therefore, phi b is equal to b into integral of dA. Integral of dA. dA means small area. So now integrating the value of area, then given magnetic flux phi b is equal to b into A. So integral of dA is equal to A, total area of the conductor. So this is nothing but magnetic flux. Understand, students? Okay, then one more explanation. On the other hand, in this case, now consider the area and perpendicular to the normal vector. So magnetic field is a constant. Here magnetic flux phi b is equal to integral of b into dA cos theta. B is nothing but constant. Magnetic field is a constant. Integral of dA into cos theta. So now here, listen it. Magnetic field, the magnetic field is uniform over the area and is perpendicular to the area. Understand, students? So magnetic field and normal vector here is perpendicular to each other. Magnetic field is perpendicular to normal vector. So what is the angle? Theta is equal to 90 degree. Theta is equal to 90 degree. What is the value of cos 90? Cos 90 is equal to 0. So total flux is also 0. So students, now write the formula only. Flux phi b is equal to BA. What is the value of integral of dA? That is nothing but total area A into cos theta. Phi b is equal to BA cos theta. So it is measured by Tesla meter square. Magnetic field, it is measured by Tesla. That is unit Tesla. What is the unit of area? Meter square. Therefore Tesla meter square. It is also measured in Weber. 1 Weber is equal to Tesla meter square. Understand, student? Next, going to what is electromagnetic induction. As I am already told you, Faraday atoms that produce a change in a magnetic field and produces current. Understand? So let us consider small circuit. This is a small circuit, consists of a cylindrical coil wire made up of several number of turns of insulating copper wire connected in series to a sensitive galvanometer G. Coil C, G is we call it is galvanometer. So students, this is a simple circuit. Now galvanometer in this circuit will not show any deflection. That is the reason there is no source of electric current inside the circuit. No source of electric current in the electric circuit. Already know what is use of galvanometer, which is directed to the flow of current. Understand? Okay. Whenever there is relative motion between the coil and bar magnet, the galvanometer shows deflection indicating the flow of induced current. Understand? When a bar magnet inserted into the stationary coil with a north pole facing, this is a north pole facing the coil, there is a momentary deflection. It's nothing but relative motion between the coil and a bar magnet. Momentary deflection in the galvanometer, this indicates that an electric current is set up in the coil. So if the bar magnet kept at rest inside the coil, the bar magnet kept at a rest inside the coil, the galvanometer does not indicate deflection. That means galvanometer value is 0. Now bar magnet is away from the coil. The galvanometer again give a momentary deflection, but in the opposite direction. Now see the terminal. This is a opposite in direction. So electric current flow in opposite in direction. Are you clear, children? Okay. Now the deflection, galvanometer deflection is more when the magnet is moved faster. Understand? If the magnet is moved faster, it gives a large deflection. It gives a large deflection due to a greater current inside the circuit. In case if the magnet is moved lesser, it gives a less deflection due to less current in the circuit. Are you clear? Okay. Then however, and reversing a magnet, that is south pole pointing toward the coil, then the result is same or obtained, but current flow in the opposite in direction. So the south pole magnet, it produced opposite in direction, current flow in the opposite in direction. If the magnet is kept stable and the coil is moved toward or away from the coil, similarly result are obtained. It is concluded whenever there is relative motion between the coil and a magnet, there is deflection in the galvanometer indicating the electric current set up in the coil. Understand, students? Okay. Then go to next demonstration. That means second experiment. The coil C1, this is a coil C1. Now taking this is a coil C1, this is coil C2. The consists of coil, this is a primary coil P. C1 is connected to the battery B with a key. Is called a primary circuit. This is called a primary circuit. While this circuit with your coil S, this is a secondary coil. We call it is C2. And a galvanometer is connected. Across connected in galvanometer is known as secondary circuit. The coil P and a S are kept at a rest in close proximity with respect one other. Proximity is nothing but nearest in space. So if the primary circuit is closed, now listen it, this is a closed circuit, the electric current start flowing in the primary circuit. At that time, the galvanometer give a momentary deflection. So listen it, when the key is pressed, that means closed, the galvanometer is connected with the coil 2. So a sudden momentary deflection, this indicates that a current is induced in the coil C2. This is because when the current C1 is increases from 0 to certain steady value, the magnetic flux linked with the coil C1 increases, hence the coil C2 is increasing magnetic flux linked with the coil C2 also increases. This causes the deflection in the galvanometer. Understand, students? Okay. Then suppose on releasing the key, the galvanometer show deflection in the opposite direction. Now see because the current in C1 decreases from maximum to 0 value. The magnetic flux linked with the coil C1 decreases, hence the magnetic flux linked with the coil C2 also decreases. This causes the deflection in the galvanometer in the opposite deflection. When the electric current becomes 0, the galvanometer show no deflection. From the above observation, it is concluded that whenever the electric current in the primary circuit changes, the galvanometer show a deflection. Clear, students? After that, Faraday realized that electromagnetic induction. Electromagnetic induction, so easy to understand. Now listen, whenever there is a change in the magnetic flux linked with the closed circuit. Now understand, student, changing magnetic flux linked with the closed circuit, it produces EMF. This EMF is known as induced EMF, because in this induced EMF flowing through the closed circuit is called the induced current. So change in the magnetic flux associated with the closed circuit, this is known as electromagnetic induction. Understand, students? Now see, whenever the magnetic flux linked with the closed circuit, that means closed coil changes, and EMF is induced, and hence the electric current flow in this circuit. The current is called induced current, and the EMF giving rise to such current is called induced EMF. This is known as electromagnetic induction. Understand, students? Okay, then Faraday discovered the electromagnetic induction conducting several experiments. Now going to first experiment, Faraday's first experiment. Now we are bringing a bar magnet. This is a bar magnet. So north pole of the magnet and the south pole of the magnet. Around the region of the magnet, there is produced magnetic field lines. If there is magnetic field, there is magnetic flux. Now Faraday experiment. So the Faradays actually move to the magnet close to the coil. At the same time, move to the magnet away from the coil. Whenever there is motion between the circuit and magnet, so we can do it in two ways. In first way, we can circuit at rest, move the magnet toward away from the circuit. In another way, you keep at a rest magnet. You move the circuit away from the magnet and close to the magnet. In either case, we can see whenever there is relative motion between the circuit and magnet, galvanometer show deflection. Galvanometer show deflection. So when I move the magnet toward the coil is nothing but circuit, the galvanometer deflection in one direction. This is a right side of deflection in galvanometer. So students, there is a current flow on the circuit. This is the induced current. Similarly, when move the magnet away from the circuit, at the same also galvanometer show deflection in the opposite direction. So whenever the motion of the bar magnet or circuit get deflection in the galvanometer. So student, there is deflection in the galvanometer when there is relative motion between the coil and bar magnet. In the second experiment, the coil C1 is connected to a battery. This is a coil C1 is connected to a battery through the key, and coil 2 C2. This is coil 2 C2 is connected to a sensitive galvanometer and kept close C1. When the key is pressed, that means closed, the galvanometer connected with the coil C2 shows suddenly momentary deflection. This indicates that a current is induced in the coil C2. This is because when the current in C1, that is primary current IP, increases 0 to certain steady value, the magnetic flux linked with the coil C1 increases, hence the magnetic flux linked with the coil C2 also increases. The magnetic flux linked with the coil C1 increases, and also magnetic flux linked with the coil C2. C2 also increases. This causes the deflection in the galvanometer. Suppose on releasing a key is a releasing, that means open circuit, the galvanometer show deflection in the opposite direction. This indicates that current is again induced in the coil C2. This is because when the circuit C1, that is a coil's current in C1 decreases. The current in C1 decreases from maximum to 0 value. The magnetic flux linked with the coil C1 is decreases, hence the magnetic flux linked with the C2 also decreases. This causes the deflection in the galvanometer in the opposite direction. Are you clear? So there is deflection in the galvanometer whenever there is a change in the primary circuit. That means primary current IP. Next, based on these studies on the phenomenon of electromagnetic induction, Faraday proposed the following two laws: Faraday's first law and second law. Now listen, Faraday's first law: whenever the amount of magnetic flux linked with the circuit, closed circuit, changes, an EMF is induced in the circuit. So student, the induced EMF lasts so long as the change in magnetic flux continuous. This is a Faraday's first law. And go to second law. The magnitude of induced EMF in a closed circuit is equal to the time rate of change of magnetic flux linked with the circuit. So student, in another definition, the magnitude of induced EMF in a closed circuit is directly proportional to rate of change of magnetic flux with the circuit. Therefore, E is directly proportional to d phi by dt. So this symbol for permittivity already you studied in first lesson, but now in this lesson we call it is induced EMF. You say simply, you say E or induced EMF. E is directly proportional to d phi by dt. Therefore, proportionality is cancelled. E is equal to d phi by dt. This is a Faraday's second law. Okay. Now calculate rate of change of magnetic flux. So, a rate of change of magnetic flux, that is equal to phi 2 minus phi 1 divided by t. What is phi 1 and phi 2? Phi 1 be the magnetic flux linked with the coil initially. Phi 2 be the magnetic flux linked with the coil after a time t. So, phi 2 minus phi 1 divided by t. According to Faraday's second law, the magnitude of induced EMF is directly proportional to phi 2 minus phi 1 divided by t. Phi 2 minus phi 1 is nothing but d phi, is the change in magnetic flux in time dt. That is, E is directly proportional to d phi by dt. Now proportionality is cancelled. A is equal to d phi by dt. Are you clear? Okay. Then, if a coil consists of n number of turns is tightly wound such that each turns cover the same area, so then the flux through each turns will be same, then total EMF induced in the coil is given by E is equal to n d phi by dt. So n is the number of turns, n phi b is nothing but flux linkage, defined as the product of number of turns n of the coil and the magnetic flux linking each turns of the coil phi b. This is phi b, magnetic flux. Understand students? This is a Faraday's second law. Rectified discovered a simple law given the direction of induced current produced in a circuit. Now tell me, what is the formula for induced current? E is equal to n d phi by dt. Already you know that. Okay, now Lenz law states that the induced current produced in a circuit always flow in such a direction that it opposes the change or cause that produces heat. So student, if the coil has n number of turns and phi. N number of turns and phi is the magnetic flux linked with each turns of the coil. Then the total magnetic flux linked with the coil at any time is n phi b. Therefore, E is equal to minus, that means oppose the induced EMF. So minus dn phi b divided by dt. So negative sign indicate that the direction of induced EMF is such that it opposes the changing or changes in magnetic flux. So this is a Lenz law. To understand Lenz law, let us consider two illustrations in which we find the direction of induced current in a circuit. So first illustration, consider a uniform magnetic field with the field lines is perpendicular to the plane of the paper. Now see, this is magnetic field is perpendicular to the plane of the paper. Plane of the paper P, we call it is P, is perpendicular to it. The pointing inward direction. Okay. These field lines are represented by cross, that is magnetic field. A rectangular metallic frame A, B, C, D is placed in this magnetic field with its plane perpendicular to the field. This is perpendicular to the field. The arm AB is movable so that it can slide toward right or toward left. Understand? Okay. If the arm AB slide to our right side, the number of magnetic field lines passing through the frame A, B, C, D increases and a current is induced as suggested by Lenz law. What is Lenz law? The induced current produced in a circuit is always flow in such a direction oppose the change or cause that produce it. This is a Lenz law. Induced current oppose this flux increases and it tries to reduce it by producing another magnetic field pointing outward, that is opposed to the exceeding magnetic field. This is a outward direction of the magnetic field. Okay. Then the magnetic lines of these induced field are represented red color circle dot. From the direction of magnetic field thus produced, the direction of induced current is found in anti-clockwise direction. This is the induced current I, by using right hand thumb rule. So students, I will tell you later right hand thumb rule. Okay. Then next, the motion of the arm AB is decreases magnetic flux. The induced current this time produces a magnetic field in the inward direction, in the direction of the exciting magnetic field. Therefore, the magnetic flux decreases is opposite by the flow of induced current. So, magnetic flux is decreases. Magnetic flux phi b is a decreaser. The induced current in opposed to the circuit. So opposite by the flow of induced current. This is a induced current. From this, it is found that induced current flow in clockwise direction. This is a clockwise direction. The next illustration 2. Already you know that circuit with bar magnet. So no relative motion between the coil and bar magnet because of no deflection in the galvanometer. Already you know that. This motion increases. That means when motion of the current is increases, magnetic flux changes, or increasing magnetic flux of the coil, which in turn induces an electric current. Flux will be changes, induced current it produced. That means induced EMF. Due to the flow of induced current, the coil becomes a magnetic dipole whose two magnetic poles are on either end of the coil, north pole of the coil, south pole of the coil. In this case, the cause producing the induced current is the movement of the magnet according to Lenz law. What is Lenz law? Oppose that cause. Oppose the change or cause that produce. Understand? Okay. What is a induced current should flow in such a way? This is a induced current. Oppose the movement of the north pole toward the coil. North pole of the coil and north pole of the bar magnet. Both are like poles are repelled to each other. Then it repels the north pole of the bar magnet and oppose the movement of the magnet. Oppose the movement of magnet. Once pole end are known, the direction of induced current could be found by using right hand thumb rule. Are you clear? Okay. When the bar magnet is withdrawn, the nearer end becomes south pole of the coil. This is the north pole of the bar magnet. This is the south pole of the coil. So both are unlike force because attract to each other. So opposing the receding motion of the magnet, thus the direction of induced current can be found from the Lenz law. Next conservation of energy by using Lenz law. So students, the basis of the conservation of energy according to using Lenz law. Now taking the coil with a bar magnet. A relative motion between the bar magnet and a coil which deflecting on the galvanometer. So students, now here induced EMF is produced. There will be a resulting resisting force on the moving magnet. It produces a force. That force is nothing but resistive force. Now work has to be done by the some external energy to move the magnet against the resisting force. So here mechanical energy is converted to electrical energy, which in turn get converted into joule heat in the coil. So that is energy is converted into one form to another form. Are you clear, children? So induced current helps the cause responsible for the protection by according to Lenz law. Now when the magnet is pushed a little bit toward the coil, induced current helps the moving or movement of the magnet toward the coil. So they start moving toward the coil without any expansion of energy. This is a conservation of energy. Then go to discuss Fleming right hand rule. Now taking three finger, thumb finger, forefinger and middle finger are mutually perpendicular to each other. So students, when a conductor moves in a magnetic field, the direction of motion of the conductor and a magnetic field, the induced current are given by the Fleming right hand rule. Now follow thumb, forefinger and middle finger of right hand are stretched out in mutually perpendicular direction. If the forefinger point in the direction of magnetic field, now underline forefinger in the direction of magnetic field and a thumb indicate the direction of motion of the conductor, then the middle finger will indicate the direction of induced current. This is an important 2-mark question. Now see, this is a right hand thumb rule. Now taking three finger, thumb finger, middle forefinger, this is a middle finger. Now thumb in the direction of motion of the conductor, forefinger in the direction of field, magnetic field, and middle finger in the direction of current. Middle finger in the direction of induced current, mind it. Now here induced current, because the magnetic field using and produced current. Are you clear? This is a very important one, Fleming right hand rule. Okay students, now you tell me the answer for these questions. What is mean by electromagnetic induction? Second question, state Faraday's law of electromagnetic induction. Third, state Lenz law. Fourth question, Fleming right hand rule. And fifth question, define magnetic flux. So students, hope you understood. Next class, continue our lesson.